Studying up for the test? Good. Excellent. I expect everybody to do better than people who wrote a similar sort of test over the summer did. You are the computer science class. I have high expectations for you. Excellent. Test. Good. So, any questions about the test or anything in particular before we get started? Speak now or forever hold your peace. Yes? Yep. The TA is correct. There are 4 questions. Yeah. Yes. Yes. When you arrive in the room, they'll be passed out on the desks. Yeah. Incidentally, just a couple of rules for writing the test in the testing room. We're going to pre-dispense the test, the syntax reference sheets. We're going to lay them out on the desks. Please, we're going to manage the seating plan in that manner. Do not move them. Sit where the syntax reference sheets are. Those are like the valid places to sit. If you violate the rules, you'll have to move. Okay? It's not like you're going to get 0 on the test, but you are going to be asked to move. It's slightly, socially awkward and embarrassing, so if you'd like to save yourself the embarrassment of being asked to move, sit where you're supposed to. Yes?
So at 3 questions and a bonus question, does that mean we answer the first 3 is 100% and the bonus is higher?
That's typically how bonus questions work, yeah. So yeah, if you answer the 3 questions which are not the bonus question, that means you'll get 100% on the test, presuming you got those questions correctly, or you did those questions correctly, with no mistakes, perfect solutions. And if you do the bonus question, any marks that you get on the bonus question will be marks that can contribute to deficiencies you may have on later tests. Make sense? The bonus marks are category limited in this course. Yes? Yes, the test will include test cases, so you can use the test cases that are provided. I always recommend testing beyond the given test cases, but it is what it is. Yes? So the thing about programming is that you can solve any problem with just if statements and while loops if you really want to. You can improve your writing speed, of course, by making good use of the functions which we've been using in class. If you take the time to actually examine the syntax reference sheet, which we are providing as an aid during the test, many useful functions are provided on that syntax reference sheet. So Yeah, pretty much any, function, like the math library is fine to use, anything, use anything that it doesn't require, downloading new libraries off the internet. Like everything, all of the basic Python libraries that come with Python are yours to use. Does that make sense? Any questions? Any further questions? Yes? You will have, if you want access to other libraries, you'll have to import them yourself. If you want to use the math library, see, you're asking me details of like the code that's given in the code stubs, and I can't cast my brain onto that. Probably anything that's necessary for the instructor's solution will already be imported. And if you want anything other than that, you'll have to import it yourself. I believe that'll be how it goes. I'm going to say yeah. We'll see how it goes. Libraries are technically unnecessary, but at least in Python. Any other questions? All right, everybody's going to get 100% then? Good. So last time we were talking about global versus local variables. I pulled up Python Tutor to give you a demonstration of this. I think that the Python Tutor demonstration is far superior to the following, 6 or 7 slides. So we'll just go through these very quickly. So if this is your Python file, any variable is in scope past its own declaration, right? So n is in scope past n, x is in scope past x, right? All of the code is at the top level of our program. Once this code is run, we can't call it again with a different input. No code reuse, no modularity, all variables are global. This is why we like to encapsulate code inside of functions. This is our well-known factorial function. So inside of this function, the scope of n is scoped to this function, x is scoped to this function, I is scoped to this function, right? This should be on that line, but whatever. So when you have variables which are declared inside of functions, including those that are arguments to that function, after that function terminates, they cease to exist. Question?
It says that you can't call it again with the different input, but like, what does that mean exactly?
So if this is just in the file, right? Well, within the context of the Python program itself, there's no ability to take this procedure, right, and reuse it within this same Python file. What you can do, of course, because these are programs and it's possible to pass information into programs using, for example, command line arguments, it is possible to rerun this program using, it's possible for this program to take command line arguments and, perform different functionalities on different data based on the command line arguments that are given. That's a bit like passing, arguments into the program itself rather than a function. But at the level of this Python file itself, you can't, in order to rerun this loop for a different n, for example, you'd have to like copy paste it down here and change the value of n, which, in general, we try to avoid copy paste as much as possible, right? If you're copying and pasting more than twice, certainly, you should be writing a function. Make sense? Even if it's a helper function. It's all about modularity, folks. So, the definition of factorial and print statements are at the top level of the code, but the red lines are local to the function. We can use b factorial function many times with different inputs. This enables code reuse and thus constitutes modular design. All right? Modularization is the golden word in your chosen field. So, if, for example, we have this function defined, we print factorial 6, factorial 4, and then we attempt to print x and n, we cannot. We end up getting a variable undefined error. X is local to the function itself, therefore, if you try to access it in the main body of the program, it will not exist. You will run into an error that will terminate your program. Make sense? Any questions? Good. However, let's, all right. So Python's a little interesting the way that it works. With respect to global variables, right? If you just use okay, so let's say we have a situation where you declare a variable in the global namespace inside of the main body of the program, right? Outside of any function. I just said the same thing 3 different ways. If you try to use it inside of this function, you will still run into a variable undefined error, despite the fact that this is a global variable, and this would appear to be a use of a global variable in a local instance, right? And this is a thing that's particular to Python. In order to be able to use in order to be able to use any global variable within a local context, you must declare it as a global variable somewhere inside the function, preferably at the top, right? So this is a version that will work. Global, right? Global res, or result, right? We set result equal to 1 here, then we call factorial. This means I would like to use the global version of this variable rather than reinstantiate it as a local variable, pretty please. And the whole algorithm proceeds on that basis. Make sense? Any questions? This is just a thing that's particular to Python. You know, slightly inelegant, but that's Python for you. Yes?
Can you do something equivalent to public get and private set variables in Python?
Wait till we talk about classes. Yeah. The way that Python does private members of classes is going to make your skin crawl. But that's, you know, anticipating a number of lectures from now. So, I've already given you guys the spiel about why you shouldn't use global variables wherever that's possible, right? So I'll just run through that again briefly. So, the thing that enables software design, like good software design, the thing that enables us to work with large programs is the principle of abstraction expressed through the practice of modularization. All right? So, when I write a piece of code, I fix the interface to it, and then I write that function in such a way that its properties are known, right? I should have some way of relating conceptually what I put into it to what I get out from it, right? So take, for example, the max function. Max takes in a tuple and outputs the maximum value in that tuple. It does more different things than that, but you know, that's one of the things that it does. It's very clean, it's very precise, it's very simple. It takes something in and gives out a predictable result. right? Every single time a global variable is used inside of a function, it is implicitly both an input and an output, right? The state of that global variable when the function is called is an implicit input to the function, and the state of that global variable after this function executes is an implicit output to this function. You'll notice that in this particular instance, it's the only output to this function, right? So basically, anytime you think you should be doing this, what you actually should be doing is formalizing that input-output behavior in terms of the actual parameters, what you call it, in terms of the formal parameters of the function for inputs, and in terms of the return value for the output. This is the accepted interface with which functions operate, right? Anytime you're using a global variable, you are working against the principle of modularization, right? The principle of modularization is the only thing that allows software to be written at the scale that it presently exists in our modern era, right? So, basically, overuse of global variables makes you look like a bedroom programmer, right? And I know, like, many of you would consider yourselves to be bedroom programmers at this point, but the whole reason you're coming to school to learn programming is so that you can elevate yourself above the class of people who learned in their bedrooms, right? That means picking up correct software design techniques such as good modularization, right? I'm actually having a problem with the 2CO3, the second year algorithms class, that group of people. Very slight side tangent. Let me complain about another class for a moment. So they had an assignment recently where they were asked to perform an operation over a data structure. And it is like a solution that works to simply take that data structure, pluck out the values contained in the data structure, swap them, and then put them back, right? But those data are contained in nodes, right? And the correct modular way of doing that is to take the nodes themselves and perform that same swapping operation, right? The reason that I had to go on a bit of a rant on the Piazza forums at these people who were all like, oh, but it works, that should be good enough. It's like, well, that's good enough for first year, you know, but by second year, we're expecting you to start picking up programming, you know, in a slightly more advanced sense than just being able to get it to work, particularly because you people are not the software engineers, you know. The software engineers just have to get things working. You people are held to a higher level of mathematical understanding of what's going on. The reason that just going into the nodes and plucking out the integers and swapping the integers and putting them back, the reason that's a bad solution is because it relies on the knowledge of the internal structure of the node. Right? Right? So it's fine, it's all fine and dandy, so long as you're not doing anything more complicated than just, you know, we were doing a sorting algorithm, just sorting a bunch of integers, right? I hate to tell it to you folks, but just sorting a bunch of integers is kind of trivial, right? It's hardly even worth doing. In a practical sense, the sorts of things you'll be sorting are, for example, database records by date, for example, right? That's something that you can actually usefully do. So, if you have written an algorithm which just picks out one integer and swaps those integers, what if somebody adds more fields to the node and your algorithm doesn't get updated, right? it's still just going to be swapping the numbers. In like a database records context, that's like taking, you know, a bunch of, you know, times that, you know, I don't know, what's some database thing? Let's talk about like tweets, since Twitter is back in the news. So let's say like Twitter is just a big database, right? That's what Twitter is. It's just a big database of people sending messages to each other. So using their solution, if you sort the dates, but leave all of the tweet contents in the same places they were, they will call that sorting it, using that solution, right? You have to actually move the records, right? So that's what I mean when I say it relies on information. It relies on knowledge of the structure of the node itself, right? But like, in order for the algorithm to generalize to any record, you have to not assume knowledge of the internal structure of the thing that you're swapping, right? Which means using the DAM interface to the linked list instead of just getting in and messing around with its private members, right? Or members that should be private even if they weren't made private. Make sense? So I'm not just telling you this for my health, it does actually matter. So anyway, that segues quite nicely into our next topic, software design. So, software design principles. Modularity / decomposition. A program is broken into parts. In the present context, we're talking about functions. In a more general context, we will be talking about classes, because of course, object-oriented programming is totally a thing. Your modules should be reasonably self-contained. They should achieve a clear purpose, and they should be reusable. Ideally, your software modules should resemble Legos. They should be small, concise, have a specific purpose, and be easy to fit together with one another. So, abstraction. Abstraction is a word that means different things to different intellectual disciplines. In this particular case, what we mean by abstraction is that a piece of software can be used without a knowledge of its internal structure, right? It's exactly the same thing I was talking about with these nodes, that people were sorting, right? When you use a library function, it's not necessary for you to know how the computer computes a square root, right? So, you don't have to understand that. You can just use the function, right? That's our goal. That's our goal with the software we write as well as with the software we use. Make sense? Questions? Cool. So, large programs will have many, many, many functions. It turns out that for very large programs, it's useful to be able to organize them. It's useful to be able to organize groups of functions into, particular units, package them with the data that they operate over. That's what a class is, right? Each function should be relatively small and be designed to do one thing only. So, for example, if we were to talk about, once again, Twitter, you would have a function to store a new tweet. So the tweet button is actually a store in database button, right? One function to record a user liking a tweet. That's just a button that increments number of likes in the database entry, right? One function to delete a user's tweet from the database, delete record from database operation. Like if you examine all of the basic Twitter functionalities, they all basically boil down to the types of things that we're going to talk about when we talk about SQL later on in the course, right? Yeah. I always say Twitter isn't scary. Twitter is just a database. It's the people on Twitter who are scary. So, so one very important pillar of good software design, aside from like the modularized structure of the software itself, is documentation. All right? If you don't tell people what your software does, how are they supposed to know? Right? We document the software in order that other people might know what our programs do, how they do them, possibly a little bit, but mostly, what can they expect for the output given the inputs, right? In Python, you have an inbuilt documentation feature called a docstring. Docstrings are produced using the following syntax. They can only be put in particular places in the file, such as underneath class definitions and underneath function definitions, and I believe method definitions as well. But you open one with 3 double quote characters, you close it with 3 double quote characters. Everything in between these is displayed to the user when they use the help function on the function that this documents. Right? So this is the mechanism by which Python documents itself and its own prelude functions and that sort of thing. When I, in a lecture or two ago, when I asked for the help information on print, it was just disengorging this information. Make sense? I believe it also includes like the declaration line as well, and you don't have to put that here. So, yeah. So, in general, documentation should contain a few things. Number one, you want to give the user the information necessary to correctly use the inputs to the function. Since this is Python, right, this becomes even more critical than in languages where the input type of input parameters must be specified. In Python, if we have factorial, right, with n here, n is presumed to be an integer, but it is syntactically legal to give this a string or a tuple or another function or a class or any number of different things could go in here, right? And any type annotations that you might put in there to try to indicate that this should be an integer are also not binding in Python. So basically, the onus then falls on documentation and common sense, right? So the types of things that you want to document about your program, assumptions that this function makes about the inputs. For example, with our make change problem, we assumed that the tuple that was input had our coin denominations in descending order, right? That is a very, very important assumption to note, because if you don't note that assumption and you put your coin denominations in ascending order, it completely breaks the algorithm, and you end up with the change made in all pennies or nickels or whatever the smallest denomination is, right? So, assumptions, requirements. If the data have, assumptions and requirements are kind of the same thing, actually. Preconditions is just a slightly more formally logic way of saying the same thing as well. Question?
Would it be like, when you're creating an assumption, would it be more common to assume that they might put an unordered list and then sort it within the function itself?
Depends on how user-friendly you want to be. In general, I think it would be a good assumption. Yeah. So that sort of gets into a larger question of software design, which is, which assumptions should I make? You know, which assumptions are good assumptions to make about, you know, the data that I'm working with, or the data that I might possibly receive from users? I would say that if you're just taking in a list or a tuple or something like that, assuming it, like requiring it to be sorted by the user before it gets to your function, it puts more on the user and less on you, when you could easily just throw a sorting algorithm in there, right? Like in previous versions of this class that I've taught, I've actually done that. I've put a sorting function as a pre-processing step before I get to the make change stuff, right? The fewer assumptions you embed in the interface to your function, basically the better, right? Unless it's like, you know, some kind of fixed data structure where you're only accessing it via specific methods and you're like maintaining a sortedness property over time, right? If you're maintaining the property yourself using the classes or something like that, then, you know, absolutely you can have one of your methods assume that the data structure is already sorted. Like, you know, if you're writing a class that performs heap sort, for example, heap sort assumes that the data is structured into a binary heap, right? The input, like the methods which add data to the binary heap are designed to maintain the binary heap properties, and it is then, and the purpose of that is so that the more useful methods that actually perform heap sort can assume that the binary heap properties hold, and they don't have to do anything to it before they actually perform the heap sort. Yes?
So if you wanted to, like, would it be possible if you want to make this just perfect? You have optional parameters, sorted equals false.
Yeah, you can do that.
Sorted, unless the person specifically says how to sort this, I've already sorted it, like, you know, be more
Well, that's also, like, I would say you could do that, or you could just pick a sorting algorithm that, you know, operates very quickly on an already sorted array. Right? That way you don't have to make that, you don't have to get the user to, you know, tell you whether it's sorted or not. It just, you know, because there are sorting, for example, insertion sort. Insertion sort's not generally a good sorting algorithm. Like it's definitely outperformed by like quick sort or merge sort and those sorts of things. But insertion sort operates in quadratic time if its processing time is proportional to the amount of disorder in the array. So if you have an already sorted array, its best case runtime is linear. So whereas its worst case runtime is quadratic. So, you know, like there's no sorting algorithm that like to check to see if something's sorted will always take linear time anyway. So, makes sense?
These are all just assumptions that we make about how the user might interact with the function.
Precisely. These are all assumptions that we're making about how the user might interact with the function. The more you take care of and the less you leave to the user, the more like the happier your customers will be, and the more smoothly development goes, basically. Make sense? That being said, there are certain assumptions that it's like absolutely like totally the user's problem. Like, for example, passing in the right data type, right? Even though Python is very loose about this sort of thing, that's generally like, that's something that you can definitely put on the user, is, you know, calling your functions with the right data type. Which is, you know, why we put that on you for the, like, the assignment questions and stuff, right? Question?
Doesn't, like, you know, the thing with Python being able to take the wrong data type, doesn't that just, like, the same with them, with the function being able to return two different data types, doesn't that just inevitably lead to faulty software being written in Python?
So the question is, this whole business of you being able to put many different data types into a function and be able to return multiple different data types from a function, doesn't this just inevitably lead to poor software design? No comment. Yes, there's like, I know I'm like the Python, I'm the intro to programming prof teaching Python who hates Python, but like hopefully you guys are beginning to have some appreciation for why you should, you know, the next thing you should do in your programming careers is put away these children's toys and learn a real language, right? So anyway, so assumptions. Anything the user needs to know to provide correct inputs, that should be documented. In the same manner, any guarantees or post conditions should also be documented. What does your function actually do to the inputs? Right? What are you calculating? Right? And of course, your guarantees and post conditions are always assumed to hold so long as the assumptions are satisfied. Make sense? Any questions? Perfect. So, again, doc strings, know them, love them, learn a better language. When you call help on make change, this is what it will output. You'll notice it does in fact copy the function prototype without you having to provide it explicitly in the doc string, and it just prints out whatever you put in the doc string, which is extremely useful. Cool. So, anywhere you get the Python prompt, you can, and you have this function loaded into memory, you can do it. You can even, right? You can call help inside of a function, capture standard output as a string, and then like do, I don't know, like language processing over it or something. You know, see how many times the word input is used over a function's documentation by just capturing the standard output into a string. The coverage of the test is assignments 1 and 2. Well, I mean the slides that assignment 1 and 2 were applied to, so that's the intro, the expressions and statements stuff. There's a little bit of light data structures in there too, because there's a little bit of light data structures in the stuff on statements, but we don't get too heavily into it. Cool? All right. So. Can you maybe ask me this afternoon or after class? Yeah, I'm sorry, but this is not the appropriate forum for me to help you with your homework. So, let's talk about recursion. All right? How many people have heard of recursion before? How many people have heard of it because I talked about it previously in this class? Yeah? How many people have never heard of recursion before? Okay, cool. Yeah, good. Well, okay. See, most of the time I'm teaching like business majors and stuff, right? So like I reflexively ask these types of things that I need not ask of computer science people. Yeah, it's true. We all know what assumption, what the thing about assumptions. Anyway, so as you've probably heard from 1KC3, roughly speaking, a recursive function is one which calls itself. If you guys have been doing any Haskell programming whatsoever, which is, you know, hopeful and probable at this point, you will have noticed that Haskell uses recursion instead of loops, right? Recursion is an alternative format for iterative processing It's kind of interesting. With respect to Turing completeness, has Dr. Farmer told you guys why Haskell is Turing complete? No? You guys have talked about Turing completeness, though. Yeah. So, in order for something to be Turing complete, you have to be able to create a non-terminating program, right? So, how do you get that in Haskell? No, it's because Haskell will complain at you if you don't include a base case, right? So Haskell uses what's called lazy evaluation, which means it only generates the data structures it has up to the point where they're actually used by something, right? So, in theory, not in practice, but, well, kind of in practice, but in theory, Haskell supports infinite data structures, right? I believe it's the repeat function will generate a theoretically infinite list, right? So recursion on an infinite list is the repeated non-terminating program. That's the equivalent of a while true in imperative languages. Yeah. Yeah, because if you have an infinite list, if you do like the head-tail bifurcation, the tail is always still infinite because it's infinite, right? Anyway, so we've already talked about the definition of factorial a few times. In general, recursive algorithms follow the inductive structure. So we have an iterative case and a base case, right? Once you guys start getting into the higher maths, you will find that many of the mathematical proofs you are required to perform, or the things you're required to prove, will require inductive arguments, right? Have you guys done proof by induction yet? Yeah? Yeah? Good. So, this is kind of a related technique, right? So, recursive definition of factorial, reasonably straightforward. You might even say it's almost a direct implementation of that function as expressed in its inductive form, right? These two cases are translated into an if statement, although not perfectly. Can anybody spot the difference? Yeah. The if statement accepts negative numbers. Is factorial defined for negative numbers?
Not for your standard definition of factorial.
Not for your standard definition of factorial, and since we're going with the standard definition of factorial, what happens if we give this guy a negative number? Yep.
It will infinitely recurse.
Yes. Because we're not testing to see whether the number is positive, another way of saying this is that we're not restricting the domain of the function to that which is defined by the function, or defined by the definition. If we put a negative number in here, it will call, like, say, -3. It'll return -3 times factorial of -4. -4 will be -4 times factorial of -5. It never hits n equals 0, right? Particularly in Python, because in something like C, well, in C you'd blow up the stack and you'd have stack overflow if you tried doing this. But assuming you didn't have a stack overflow, eventually the integer would wrap around back to 0, and this would actually terminate at some point. The thing that Python does is, to avoid overflows, it actually appends more bits to your integers. It sort of expands your integers the more you use them dynamically while the program is running. So in theory, In Python, this infinite recursion is truly infinite. Make sense? Question? Oh, I thought I'd use a real laser today. I don't know, I don't want to keep running back the thing. I wanted to get, I'm seeing if this is like faster and I can cover more slides by not having to run back and forth. The lightsaber is still over there. So, anyway. Any questions? Yes? You don't get how the n value... I'm glad that you've asked this question. I'm going to pull out the lightsaber because this is for emphasis. So, this is an imperative programming language. When we try to evaluate this statement, this call to factorial opens up a new stack frame, right, which is placed on the stack. 5 is passed into that stack frame, replaced with n, and then we execute this function, right? We, of course, travel to this statement in the else case. We are attempting to evaluate this expression, right? In order to evaluate this expression, we must evaluate this function to find its result, right? Right? Yeah, so this function call will put another instance of the same function on the call stack, right? So, but of course, before we do that, n has been substituted for 5. This inner expression has been evaluated as 4. So, when we're calling factorial on 4 rather than 5, it's a new stack frame, right? So, because we've now asked for what is the factorial of 4, we jump back up to here, execute this in the new stack frame, right? 3, execute again. 2, execute again. 1, execute again. 0, execute. Hit this guy, right? This 1 does not require another call to factorial to evaluate, right? So, it just returns 1. Now, you've got, at that point, 5 pending expressions that you're evaluating, all depending on the results of sub-expressions, right? So, this guy gets passed back up, solves the expression wherein factorial of 0 was called for. That is the one to calculate factorial of 1. Right? So, that allows factorial of 1 to be calculated. The result of that is passed to the expression that is calculating factorial of 2. That is passed back into the expression calculating factorial of 3, etc., etc. The return values just keep propagating back up the function call stack until it reaches this guy, the original calling function, at which point you have the answer. Does that make sense? Cool. Question?
So does Python not do tail recursion like Haskell?
Say again?
Does Python not do tail recursion like Haskell?
You can do tail recursion like Haskell. In this, we're going to focus on numerical examples like factorial and the Fibonacci sequence. Yeah, no, you absolutely can, take a list and, pop the head off of it, process it, and then recursively call on the tail. Absolutely, you can do that. You just can't do it with pattern matching. So, again, different languages for different purposes, right? Haskell is more efficient because it has that inbuilt pattern matching, right? For that particular purpose, anyway. Yes?
I just wanted to comment because coincidentally, I actually just searched this up a minute ago, so I know the answer.
Okay.
So Python, you can do tail recursion in Python, but it doesn't do tail call elimination, so the stack will just overflow if it goes on for too long.
Yes. Yes. Yeah, exactly. And incidentally, the recursion limit typically, I believe, is 500. So one of the yeah, okay, just give me 1 more minute, guys. One of the interesting things about Haskell is everything, like, because everything uses recursion, right? If it were just slapping stack frames on the stack for every instance of recursion that it performs, then that's not a good solution for Haskell because it relies on recursion so frequently. So it uses alternative mechanisms in order to process that. I'm personally not an expert in it, but if you'd like some information on how particularly Haskell handles recursion, I recommend you talk to Dr. Call, at least when he's not on sabbatical. All right? Thank you very much, everybody.